So in the previous video, we showed that this relationship is not true in general. We proved it. You cannot say that integration of E dot ds around a closed contour is equal to mu naught integration of J dot dA for any surface bounded by the contour. And the reason was that if you calculated this integration of J dot dA through different surfaces bounded by the same closed contour, you get different values. So this equation like this doesn't make sense in general. So the question we asked last time at the end of the video was, can we find an expression for a surface integral that is the same for absolutely any surface that you choose that's bounded by the same closed contour? Is it possible to find an integration like this, a surface integral like this? The answer is yes. So let's go back to what we did before. We took any two surfaces and we said that there's some closed volume bounded by these two surfaces. And we looked at the conservation of charge equation and we derived this. So this is something we've derived before. I'm not going to derive it again here. Now, if you have this equation, how do you think we can proceed? Remember what we're trying to find. We're trying to find a surface integral that's exactly the same no matter what surface you choose. You choose surface number 1 or surface number 2 or surface number 3. There are infinite number of surfaces bounded by the same contour. How do you think we can proceed at this point? It's better to pause the video and try to think about it. Well, what you should realize is this Q inside. This gives the key to the problem, because remember Gauss's law, what it says. It says that if you integrate E dot dA around through any closed surface, it should equal to the charge inside over epsilon naught. So this is a clue where we can replace this charge inside by some surface integral and see what happens. And we know that Gauss's law is always valid, so for any situation. So it's very nice and very easy to do this, and it's valid to do this. So we can let's put Q in on one side. You get Q in is epsilon naught integration of E dot dA through the closed surface. And if minus dQ in by dt, because that's what's in this equation, then you just take minus dQ in by dt here, you get the minus sign, you get the epsilon naught, and you get d by dt of this integral. So let's put it to the equation. We got rid of the q inside and we put instead of it this part here. Now look at integration of E dot dA through the closed surface. Again, when we talk about a closed surface, the area vectors have to point from inside to outside. Okay, that's for integration of E dot dA. But we can always write integration of E dot dA through the closed surface as an integration over surface number 1 plus an integration through surface number 2, such that the dA vectors are pointing from inside to outside. And we can do the same trick we did before for surface number 1 specifically, because we want the right-hand rule to give us the direction of the area vector to be this way, not outwards. So for surface number 1, we replace dA out by minus dA. Surface number 2, we don't change anything because already dA out is in the correct direction, where you use the right-hand rule to get the relationship between the ds vectors and the dA vector. So let's replace dA out by, you get that, and back into this equation, you get these two integrals. Now you can see here how we can find the surface integral we're looking for. You have here integration over surface number 1 of J, and you have here integration of E dot dA through surface number 1. So let's keep those two on one side. Here you have integration of J dot dA through surface number 2, and here you have integration of E dot dA through surface number 2. So let's bring this one onto this. So we have here integration of J dot dA through surface number 2 plus this integral over surface number 2 is equal to the same expression, integration of J dot dA through surface number 1 plus the same expression through surface number 1. So that means we've been able to find a surface integral, which is this whole thing, this whole expression, no matter which surface you calculate it through, whether you calculate this through surface number 1 or surface number 2 or any of the infinite surfaces that are bounded by this closed contour, you should get the same answer. So this gives it says that it's plausible that we can replace this surface integral which we showed doesn't work for any surface, we can replace it by this integral for any closed surface, because we showed just now that these two terms, when you calculate these two terms through any surface bounded by the closed contour, it'll give the same answer. And so we can say it's plausible that we can write down now integration of B dot ds equal to this, not equal to that. That's exactly what we're going to do. And so this is now an equation that's always correct. It's always correct, and it's consistent with the local charge conservation law. So this is one of Maxwell's equations. This is the modification that you have to do to Ampere's law to make it correct, always correct. Ampere's law that we took before was this part. Turns out you have to add this term to it for it to be consistent. Consistent in the sense that if you evaluate this surface integral, these two terms, through any surface, you get exactly the same result, which has to be the case, or else, because this has to be one single number. This integral has to give you one single number. You can't calculate this through different surfaces and get different answers. So it's consistent, and of course the test is if we take this to be one of Maxwell's equations that's always correct, and take it with the other three Maxwell's equations and see what consequences come out of it, it turns out that they always agree with what you get experimentally. So this is actually one of Maxwell's equations, and this is the term that we had to add to make it work.